Hello, my name is Steve Miller and I'm the Technical Marketing Manager for Physical Modeling at the MathWorks. In this presentation, we're going to see how we can develop aircraft power networks using model-based design. Here are the key points of this presentation. First, we're going to see that you can configure your model to balance model fidelity and simulation speed. This is key to an effective use of simulation, making sure that your model level of fidelity matches the task that you're trying to perform. We're also going to see how you can accelerate your simulations using optimization algorithms and parallel computing. We'll see how we can distribute simulations to multiple cores on my machine, accelerating tasks such as estimating parameters and parameter sweeps. And finally, we'll see how you can accelerate your development by automating simulation and analysis tasks using MATLAB. We'll see how we can use MATLAB scripts to perform harmonic analysis and document the results of any task performed in an automatically generated report. Here is the agenda for our presentation. We'll first have an overview of the aircraft power network model. We'll see a list of our simulation goals and look at the development process we use to develop the model. We'll then go through that process, including the initial design where we refine the requirements, the detailed design where we look at the individual components on the network, and then the final phase we will use the simulation results from the detailed design to tune our abstract model. Finally, we'll see how we can automatically document the results of all of these phases in a report. Here is a schematic of the system that we're developing. It's a half-aircraft model that includes a generator, an AC bus with different AC loads, a transformer rectifier unit, a DC bus with different DC loads, and a battery. Breakers connect each of the components to the network. As they open and close during a flight cycle, conditions in the network will vary. We want to analyze this half network under these varying conditions. A full aircraft model would include other components. We have not included them in this half aircraft model, for we only want to analyze the interactions between these components. This is a common practice in the aircraft and marine industries. The goals that we have for our simulation are to analyze this network. We'll want to determine the power requirements for the different components on the network, as well as the power lines that connect them. We'll want to analyze system interactions between the multi-domain components, including electrical, mechanical, hydraulic, and thermal effects. And at a more detailed level, we'll want to perform harmonic analysis. We'll want to analyze the power quality under varying conditions, and look at the voltage and current at different nodes in the network. This set of simulation goals can be best fulfilled with models of varying fidelity. We're going to see as we go through the development process that we will have an abstract and a detailed model. When we look at the simulation results from these variants, we'll see that the results from the system level and detail models match. If we look closely at the simulation results, we can see that even with the dynamics due to the power switching in the detailed variant of our models, that matches the results from the abstract version. This allows us to iterate rapidly at the system level and also perform detailed analysis of the electrical system. With this, we can achieve our goals efficiently. Here is the model that we're working with. We have created multiple variants for each component in the network. We will select which variant to use based on the task that we're performing. As we are exploring power generation options, we can substitute in an integrated drive generator, a variable speed constant frequency generator with a cycloconverter, or with a DC link. We can use an abstract or a detailed version of the AC components on the AC network. Similarly, for the DC network, we can use a variant that is detailed, abstract, or one that includes effects of other physical domains, such as mechanical, thermal, and hydraulic. I'll now switch over to the model so you can see how this is done. Here is the model that we're working with. You can see the generator, distribution network, and the components on the network. The model is currently configured to run with the abstract version of the components. The actuator is modeled simply by specifying the active and reactive power that this component consumes. If we configure this model to use the detailed version of the component, the actuator is modeled using an electric machine. We have a permanent magnet synchronous machine, converters, and a DC bus, as well as a control system. If we look at the transformer rectifier unit, we can see that it is modeled using transformers and universal bridges that use power electronics. We can also select a variant of this system that includes effects of other physical domains. Here you can see that we have hydraulic pumps, hydraulic loads, and in this component we can see a thermal network, where we can see how the behavior of this component varies as the temperature in the system varies. Our generator is modeled using a synchronous machine, and we have a control system to specify the field voltage for that machine. The flight cycles are chosen using a MATLAB variable called flight cycle num. And here we can see the data from the MATLAB workspace that controls when the different components are connected or disconnected from the network. This MATLAB plot shows when the components are enabled or disabled. If we configure our model for the abstract version, we can use this script to run this model and test it against 3 different flight cycles. So you can see we are running flight cycle 1, which tests the system under varying conditions. We'll then automatically configure the model to test with a different flight cycle and rerun. And at the conclusion of these 3 tests, we'll open up a report that shows the results of these tests compared to previous runs. So here you can see in the report screenshots of the model, screenshots of the scopes showing the speed, voltage, and the power generated by the generator, plots against tests previously run, and the results of power quality analysis. In this demonstration, we have seen how we can model an aircraft power network, configure it so that the level of fidelity matches the test that we are going to run, and automatically run tests for different flight cycles and document the results of those tests. Balancing model fidelity and simulation speed is key to the effective use of simulation. As you add more details to your model, the amount of time it takes for the simulation to execute will increase. It's important to configure the model to match the task that you're performing. When we're interested in details such as power quality, we'll include effects such as power electronic switching and realistic loads. However, when we're interested in effects such as the power generated or consumed by different components in the network, we'll use phasor simulation, abstract loads, and average voltage models. Using MathWorks products, you can select the right level of detail for the task that you are performing. To execute our design process efficiently, we're going to need abstract and detailed versions of our component models. Here are how those variants fit into our development process. First, we're going to refine the requirements with the abstract version of our model. We'll then use that refined version of the requirements to develop the detailed design. We can combine the detailed and abstract versions in our model to do verification tests and combine it with the control and mechanical systems. And finally, we'll use the simulation results from the detailed model to tune the abstract model. This will give us a model that executes quickly and produces accurate results. You can see that these 2 variants, the system and detailed versions, are complementary. The work we do with the abstract model to refine the requirements reduces the number of iterations required in the detailed design. This speeds up our development process. The simulation results from the detailed model give us an abstract model that produces accurate results and executes quickly. This allows us to match the level of detail in our model to our simulation task. Many companies around the world use model-based design to develop complex systems. Airbus develops their fuel management system using MATLAB and Simulink. This system contains more than 20 pumps and more than 40 valves. You can imagine the number of different failure scenarios that could occur. Using simulation, they're able to run more than 100,000 tests each weekend. This gives them the confidence that no matter what the failure scenario is, their control system can handle it. Now that we've seen an overview of our model and our simulation goals, we'll go through the design process. We're first going to use our abstract model to refine the requirements for our system. These refined requirements will be used for the detailed design. In this demonstration, we're going to see how we can integrate the requirements document into our development process. We have a large requirements document that specifies all of the requirements for our entire system. It is difficult to compare this with the overall design, to verify that the design is meeting those requirements. Using Simulink verification and validation, we can directly link the requirements document and our simulation model. We can create links from the simulation model directly to the requirements document. This makes it easy for us to verify which requirements this portion of the model is fulfilling. This link is bidirectional, so that if we are looking at the requirements, we can quickly jump to the model to verify how that requirement is being fulfilled. I'll now switch over to the model so you can see how this is done. Here is the model that we're working with. It's an aircraft power network that has a generator, AC bus, AC loads, as well as a transformer rectifier unit and components on a DC bus. We would like to compare this design to the requirements. To get to the requirements, I can simply right-click on the block, select the requirements entry, and click on this link. This brings me to the Word document that lists the requirements, and I am brought directly to the section where the requirements are listed. To add a link between the document and the model, I can simply highlight the text and then right-click on the block and select Add Link to Word Selection. You can see that a link has been added from Generator Requirements that goes to the generator. So now when I look at the Requirements option, you can see that we have the link to Generator Requirements. This is a bidirectional link, so if I click on this link for the transformer rectifier, you can see that the block is highlighted. With these links, the requirements document is integrated into the development process, making it easy to compare the design to the specification. In this demonstration, we have seen how we can integrate the requirements document into the development process. Now that we've integrated our requirements document into the development process, we're going to refine the requirements for the power network, specifically the requirements for the operating peak and design loads for the generators and lines. We'll want to test this under a wide range of network conditions, so flight cycles where different combinations of loads are turned on and turned off. Since we're only focusing on the power, we're going to neglect power electronic switching. To do this, we're going to use abstract models and abstract simulation methods. This will mean that we're going to configure the model to remove a lot of the details that we don't need, so the simulation runs quickly and allows us to test under long flight cycles. In SimPower systems, you can select from different simulation modes. You select your simulation mode based on the task that you're performing. Continuous simulation mode uses a variable step solver. This means that the step size will shrink to capture events that occur in your simulation. This is a very accurate mode of simulation. However, the speed will depend on the number of continuous states and dynamics. A very large system with many events may simulate slowly, as the solver will need to use a very small step size to capture all of the events. Discrete simulation mode uses a fixed step size. It performs fewer computations per step and can step over some of the events in your simulation. This is a very scalable mode of simulation and is good for large systems. However, you'll need to verify that the step size you choose is small enough to capture important events in your system. Finally, phasor mode uses a simplified set of equations to capture the amplitudes of voltages and currents in your system. It represents the voltage and current as a phasor with simplified algebraic equations. This is a very fast simulation mode, but only provides a solution at a specific frequency. For our tests of power consumption, we're going to use phasor simulation mode. In this demonstration, we're going to see how we can select the simulation mode in SimPower systems. We have a single-phase AC circuit, and we wish to analyze both transient effects and just the magnitudes of the circuit voltages. To do this, we're going to select the SimPower system simulation mode appropriate for the test we wish to run. You can select the simulation mode in the Power GUI. If we test this system with all three simulation modes, we can see the effects that are captured and see that the phasor mode is much faster than the other two modes. I'll now switch over to the model so you can see how this is done. Here's the model that we're working with. We have an AC source that goes through a series of resistors, capacitors, and inductors. There is a breaker in the circuit that will open after a period of time and then close again. If we run the simulation, we can see how the simulation performs in continuous mode. You can see that the oscillations that occur as the breaker opens and closes are captured accurately. We'll now switch to discrete mode. We double-click on the Power GUI block and click on the Configure Parameters button. Here we can select discrete and phasor. I'll switch to discrete mode, press OK. You can see that the simulation mode has been updated to discrete, and I will rerun the simulation. You can see that the results look nearly the same. I can also configure this to run in phasor mode. So I'll select the phasor option, select my frequency. Again, the solution is only calculated at a certain frequency, and then I will rerun the simulation. You can see that only the magnitudes are captured. Double-clicking on this subsystem will run a MATLAB script that will execute the simulation using all three simulation modes. Here you can see the results are plotted on top of one another. If we look closely at the results for the voltage and current, we can see that the discrete results are close to the continuous results, but not identical. If we look at current, we can see that there is a spike here that's not quite captured by the discrete mode. And we can see that the phasor simulation only captures the magnitudes. If we look at the step size, we can see that the phasor simulation only took 56 steps, whereas the other modes took many more steps to complete. This enables the phasor simulation to run much faster than the other two modes. In this demonstration, you have seen how we can select the simulation mode in SimPower systems. In addition to selecting the proper simulation mode, we need models at the right level of fidelity. In order to refine the requirements for the power of the components in the power lines, we're going to use generic abstract models. The dynamic load block allows us to specify the active and reactive powers that the components on the network consume or generate. We're going to define the active and reactive power based on the initial set of requirements that are in our document. For the source, we're going to use an ideal source. This will set the voltage on our network, and we can use this to size the generator to figure out how much power it needs to produce. In this demonstration, we're going to see how we can use simulation to refine power requirements for generators and lines. We have an initial set of requirements, including the rated power and power factor for components in our network. We also have a range of conditions this network can expect to encounter. We want to refine this initial set of requirements by testing the network under a wide range of conditions. We're going to do that by configuring the model to run with abstract loads and sources so that we can test it under a wide range of conditions. We'll configure the model to use abstract models of the AC loads and the generator and see the power that is generated or consumed under this wide range of conditions. I'll now switch over to the model so you can see how this is done. Here is the model that we're working with. You can see the generator, AC bus, and components in the AC network. Double-clicking on this subsystem, we will configure this model to use the abstract variants of our components. If we go into this subsystem, we can see that we have simply specified the active and reactive power that this component will draw based on the initial set of requirements we have been given. We are going to configure the generator to use an ideal source. If we go into this subsystem, we can see that we are using an ideal source that will maintain the voltage required on our network, and we will be able to measure how much current this component must generate in order to meet the requirements of the components on the network. On this scope, we will be able to plot the apparent power. This will show us the power that the generator must generate and the power that each of the power lines can be expected to experience. I'll run the simulation, and we'll see that this 40-second simulation, under which we test a variety of conditions, completes very quickly. And we can see the power requirements for each of the lines and the generator in our system under a wide range of conditions. In this demonstration, we have seen how we can use simulation to rapidly test a power network under a wide range of conditions to verify power requirements. We will now move on to do the detailed design of the components. We will use the refined set of requirements to do the detailed design, and we will combine this detailed model with other components in our system to test for integration issues. There are a range of options for generating power in an aircraft. Typically, the generator is driven by a connection to the gas turbine. The turbines will rotate at a varying frequency. If the AC network is to be held at a fixed frequency, then a conversion from that variable speed shaft on the turbine to the constant frequency in the network either has to be done by an integrated drive generator before the actual electrical generator, or by using power electronics to convert the variable frequency AC to a fixed frequency AC. There are also wild frequency systems where the frequency on the AC network is allowed to vary, and the power conversion is done at the loads on the network. Each of these options require a generator and power electronics to convert that power. SimPower Systems provides a machines library that includes components such as synchronous machines and asynchronous machines. There are many parameterization options for these machines that allow you to configure the component to match what you will put in your final system. There are also preset models to accelerate this process. To help you balance the trade-off of model fidelity and simulation speed, you can enable and disable effects in your components. There is also a range of power electronic models that cover many different devices. To help you drive those, there are subsystems that help you generate pulse-width modulated signals. Configurable bridges allow you to set up your network and then select the device type. And there are device options that are at a more abstract level and will increase simulation speed. You can log internal measurements from these bridges and view them on a scope. In this demonstration, we will see how we can model different options for generating power. We have a gas turbine that spins at a variable speed. That turbine can be used to turn a generator shaft and produce variable frequency AC. Different configurations of power electronics can convert that variable frequency AC to a fixed frequency AC. We would like to evaluate these different options. We can do that using SimPower systems. We can model each of these systems and plot the results of simulation under different conditions to evaluate which option would be the best for our system. I'll now switch over to the model so you can see how this is done. Here is the model that we're working with. The variable speed from the gas turbine is used to drive a generator, and a cycle converter is used to produce fixed frequency AC power. If we run the simulation, we can see how this model performs. The upper signal is the variable speed from the gas turbine. You can see that the frequency is varying. This yellow signal is the voltage that is one of the phases of the voltage that is produced by the generator. This fixed frequency AC is constructed from the input signals using power electronics. At the bottom we can see the current that is drawn through the diodes. If we go into the model, we can see how the system is constructed. This is our variable AC source. And here we can see that we are using transformers and power electronics to construct the signal, the fixed frequency AC. We select between the different phases and the polarity of the phase in order to generate that signal. A control system is used to control the firing of the power electronics. If I go to the top level and double-click on this subsystem, I can produce a plot that shows how this signal is constructed. If I zoom in horizontally, you can see that the pink line approximates the fixed frequency AC that we're looking for. And power electronics are used to select between the three different phases, the green, red, and blue lines, and the opposite polarity is selected when it is closer to the sine wave that we are attempting to produce. You can see that the output signal is fairly noisy, so we would probably need to use active filtering in order to get this to a form that would be good for our AC network. Now let's look at the other version, which includes a DC link. Similar concept, variable frequency is driving our generator. However, instead of converting directly from AC to AC, we're going to use a rectifier and inverter to convert the variable frequency AC to a DC signal, and then use the inverter to convert that to a fixed frequency AC power. So now I'm going to open these plots and run the simulation. And you'll see again, the top plot is the variable frequency input. You can see that the output frequency remains fixed, and that is due to the power electronics in the rectifier and the inverter. If I run the simulation again, we'll take a look at the DC signal, and you can see that the DC on that portion of the network will rise and fall as the frequency changes. However, the fixed frequency output remains at the desired frequency. Since this design is working better, we're going to increase the level of fidelity. We are currently using an ideal source. Now what we'll do is we'll select a variant where we include the synchronous machine. So now we have a synchronous machine connected to our power electronics. We're going to rerun the simulation and see how the system performs. Here you can see that the output frequency is still fixed, but we can see that there's a bit of a problem at the generator. The power electronics are drawing different levels of current at different phases of the cycle, and this is resulting in that the voltage on the phases of the generator does not follow a clean sine wave signal. We could resolve this problem by taking this transformer and replacing it with zigzag transformers, and that would allow us to compensate for the current being drawn. However, this model did give us an opportunity to compare and contrast two different options for generating power in our network. In this demonstration, we have seen how we can model different power generation options using SimPower systems. Now we'll look at how we have defined the AC loads in our network. Our network contains lamps, a hydraulic pump, and an actuator, and these have been modeled using blocks from SimPower systems. There are a number of options for modeling AC loads, and some of the components are listed here. Each of these different blocks in SimPower systems includes configuration options to help you adjust for different configurations of the component, as well as adjusting the level of fidelity in your model. I'll switch over to the model so you can see how these are integrated into our network. We have configured our model to run with a detailed version of each of our components. Going into the lamp system, we have simply modeled it as a constant power RLC load that simply has the active power as specified in the requirements document. The hydraulic pump has been modeled as an AC induction motor, and you can see we have measured a number of values associated with that to see how it performs. Our actuator is modeled as a synchronous machine, or a motor drive, where we have the electrical machine, the power converters, and the control system. You can see here that we can configure the level of detail in this model depending on our simulation needs. Simulating with a discrete mode and with our detailed versions of our components allows us to see a lot more about what is happening in the system. If we go into the scopes and look at the current and voltage drawn by the generator, we can see how the current drawn by the generator varies as different loads come on and off the network. And if we zoom in more closely, we can see what the sine waves look like. And we can see that these are not perfect sine waves. There are little notches here and there as the power electronics are switching on and off. Looking at simply the voltage from phase to phase, we can see this in a bit more detail. So we have many options for modeling our AC loads, and by simulating with those detailed versions and with the discrete mode, we can see a lot more about what is happening in our network. One of the tasks we will perform with the detailed version of our model is to analyze power quality. As we load up our system, that can cause a distortion of the supply voltage waveform. So this is a perfect sine wave, and this is what the generator would produce if our loads never changed. However, as we increase the number of loads and the number of power electronics that are turning on and off, this supply voltage waveform can become distorted, where you can see these little bumps. These bumps in the supply voltage waveform can cause problems. It can cause higher heating in the generator as the power electronics turn on and off. It can create high neutral currents, and it can create unnecessary switching in power electronics as they aren't expecting to see these ripples in the voltage waveform. Total harmonic distortion provides a measure of AC power quality. It is important to measure this under varying network conditions because the power quality will vary depending upon which components are turned on and turned off. It's easy to measure this using MathWorks products, and we can automate this and test under a wide range of conditions. In this demonstration, we're going to see how we can analyze power quality using simulation. We have a model of an aircraft electrical network. Due to the different loads in the network, the voltage waveform produced by the generator is distorted. This causes a degradation in power quality. These loads are disconnected and connected to the network at different times during a flight cycle. We want to analyze the power quality within the network under these various conditions. To do that, we're going to use MATLAB and SimPower systems to automate the calculation of total harmonic distortion. We can perform this calculation interactively using a GUI or automate it using a MATLAB script. I'll now switch over to the model so you can see how this is done. Here is the model that we're working with. Our aircraft power network consists of a generator, an AC bus, AC components on the network, as well as a transformer rectifier unit with a DC bus. We would like to measure the power quality at different points in the network under different conditions. To start, I'll show you how to do it interactively for just the generator, and then I'll show you how to automate that process using MATLAB. First, we're going to run the simulation to collect the data we need to calculate total harmonic distortion. This plot shows the line-to-line voltage coming from the generator, and you can see it is not a perfect sine wave. That means that there is the power quality on the network is affected by the components on the network. At the conclusion of the simulation, we will use FFT analyses to calculate total harmonic distortion. We'll double-click on the Power GUI and open up the FFT analysis tool. Here you can see it has automatically loaded the data that I just recorded from my simulation. We will select the FFT window, specify the fundamental frequency and the range, and then we will display the results. Here you can see that the total harmonic distortion is 2.73%, and here you can see the contributions at the different orders. This shows us how we can calculate total harmonic distortion interactively, but we would like to automate this process so we can calculate it under various conditions and at different points in our network. To do that, we'll use a MATLAB script. Here you can see a MATLAB script where we have used the command power FFT scope to calculate total harmonic distortion. Here we've specified a range of test points, so during different drive cycles at different times corresponding to conditions where we want to measure power quality. I will now go to the command window and run this script. It will advance through the 20 points and calculate and plot the total harmonic distortion. So you can see there are conditions where the total harmonic distortion is very low and other conditions where it is high. Using this automated test, I could identify conditions that cause concern, configure the model, and then see if I can improve the powering quality under those conditions. In this demonstration, we have seen how we can analyze power quality in our network. Now we'll look at some of the options we have for modeling DC loads. We can create models that include pure electrical and multi-domain options. Our DC network includes the transformer rectifier unit, as well as lamps, heaters, fuel pumps, and a battery. A variant that we have created looks at the integration issues that could result when the effects from these other domains are included. Our heater includes an electrical and a thermal network to integrate how this behavior of this component varies as the temperature changes. Our fuel pump includes a mechanical and a hydraulic network. This allows us again to figure out what the effects in the system will be when the effects from these domains are included. I'll now switch over to the model so you can see what this looks like. Here is the model that we're working with. You can see that currently our transformer rectifier and DC network is purely electrical. We have simplified electrical models for the components on this network. We can select a variant of the system that includes effects from other domains. Here you can see now that we have the same components, but instead of a purely electrical model, we have incorporated other domains, such as a thermal network to account for the change in behavior due to temperature, and here you can see a hydraulic network that accounts for hydraulic effects from the pumps and other loads in the system. The components that you see in these models have been drawn from the Simscape Foundation libraries, so you can see electrical, hydraulic, magnetic, and other domains are covered here. Using these libraries, you can incorporate effects from other physical domains into your system. You can integrate physical effects from other domains into your electrical networks. The Foundation libraries in Simscape include components from other physical domains, such as hydraulic and thermal. Using these, you can create more realistic loads for your network and then more accurately determine the conditions that your components will see. By combining these foundation elements, you can create complex mechanisms. And you can create new components and domains using the Simscape language. For more advanced components and parameterization options, look at the Simscape add-on libraries. Here you will see more advanced components with more advanced effects, such as efficiency losses and thermal effects. You can also model three-dimensional mechanical systems using SimMechanics. Now that we have performed our detailed design, we will use the results of the detailed simulations to tune our abstract model. This will give us a model that runs fast and produces results that match the detailed simulation. We started our development process with abstract models of our components. Now that we have a detailed design, we'd like to make sure that those abstract models produce similar results. The green line is based on the initial requirements that we received. What we would like to have is an abstract model that produces this blue result, which closely matches the simulation results here in red from the detailed model. To do that, we're going to specify the active and reactive powers for our abstract models using an input signal. And instead of using simple single values for active and reactive power, we're going to create a parameterized model and tune these parameters such that the active and reactive power match what we got from the detailed simulation. In this demonstration, we're going to see how we can tune abstract models to match the results from detailed models. Here is our situation. We have an abstract model of a component in our electrical network. When it is stimulated with this control signal, these are the results we get for active and reactive power. When we stimulate the detailed model of this component with the same signal, these are the results that we get. We need the abstract results to match the results from the detailed model so that we can use the abstract model in rapid simulations for system-level design. What we're going to do is automatically tune the parameters in the abstract model until the results match. Simulink Design Optimization can automatically vary these parameters until the results from the abstract model match those from the detailed model. Here are the steps that we'll go through to tune these parameters. First, we'll import measurement data from the detailed model and select the data for the estimation. Next, we'll identify the parameters and their ranges. Then, we will perform the parameter estimation, where Simulink Design Optimization will tune these parameters until the results match. I'll now switch over to the model so you can see how this is done. In this model, we have the measured data from the detailed simulation and our abstract model. When we look at this scope, we can compare the results. The yellow line is the data raw from the detailed simulation. You can see because of the power switching, there is a lot of dynamics in that signal. What we would like is that our abstract model produces what we see on this pink line, the filtered result. Currently, our abstract model, when stimulated with the same control signal, produces this blue line, which does not match for active and reactive power. Our abstract model contains a number of parameters that we can tune in order to make these models match. We'll use Simulink design optimization to tune them automatically. I'm going to switch to this model where we'll do the tuning. So here when I run the simulation, you can compare the filtered data or the reference from our detailed model and the abstract model. And again, here are the parameter values that we can tune to make them match. I'm going to open Simulink design optimization and we'll perform the optimization. Here we can see the test data that we have imported. This is the reference data from our detailed simulation. You can see the active and reactive powers plotted here. The next thing that we need to do is to select the parameters that we wish to tune. Here you can see we have selected 3 parameters from our abstract model that we will tune. Now we can run the estimation. So currently the model is being simulated, and after each simulation, Simulink design optimization will compare the results between the two, figure out how it should change the variables in order to make them match better, adjust them, and rerun the simulation. So each time the simulation blinks, Simulink design optimization is testing a new set of parameters. These simulations are being executed one after another. If we wanted to, we could run these simulations in parallel, and that would accelerate the estimation process. Even if I knew which values I wanted to test, I couldn't test them this quickly because it is automatically updating the values after each run. Simulink design optimization also calculates how sensitive the model is to certain parameter values, allowing it to make quicker and more efficient adjustments to the parameters. You can see that after this short period of time, the reactive power is matching more closely and active power is getting there. These parameter values affect these different results in different ways, which makes this a challenging estimation. In this demonstration, I'm only tuning 3 parameters, but I could tune a much larger set. It depends on how complex your system is and its parameterization. If we look at these plots, we can see how the parameter values have evolved over time, and we can see here just the latest round of how close they match. So at this point, Simulink design optimization has gotten as close as it can to the results, and this is much better than our original estimate. So we can continue in our design process using this tuned version. In this demonstration, we have seen how we can use optimization algorithms to tune abstract models. You can accelerate your development process by distributing simulations to multiple cores or processors. If you have a simulation task that requires many simulations, such as a Monte Carlo analysis or testing many flight cycles, you can just run those simulations in parallel by distributing them across multiple cores on a single machine or distributing them across a computing cluster. In many cases, it will be as simple as from changing our script from for to par for. This can result in a dramatic speedup for sets of simulations. In this demonstration, we are going to use parallel computing to accelerate a set of flight cycle tests. We have a model of an aircraft electrical network. We would like to test this network under a wide range of conditions, including different flight cycles, faults, and weather. We're going to use parallel computing to speed up those tests. We're going to use MATLAB to configure the different tests we wish to run. Then we will distribute the simulations across multiple cores on my machine. We'll see that the series of tests runs much faster when run in parallel. Here are the steps that we need to go through. First, we will open a pool of MATLAB sessions using the command MATLAB pool. Next, we will generate the parameter sets corresponding to the tests we wish to run. We will then run the simulations serially, one after another, and then compare the amount of simulation time to when we run those in parallel. I'll now switch over to the model so you can see how this is done. Here is the model that we're working with. We have an aircraft power network with a generator, an AC bus, AC loads, a transformer rectifier unit with a DC bus. We want to test this network under a range of flight cycles. We configure which flight cycle is selected using this MATLAB variable. And if we plot the flight cycle, we can see that the different loads are connected and disconnected at various points. This plots just the first 40 seconds of the flight cycle. The data that we have covers 10 minutes. This MATLAB script will walk us through the steps we need in order to run these tests. First, we need to make sure that our model can be run in rapid accelerator mode. So we'll use this command to generate a rapid accelerator target of our model. Next, we will generate the parameter sets that we need in order to test the different flight cycles. In this case, there are 8 flight cycles we wish to test. Using the command MATLAB pool, we will open a set of parallel sessions on my machine. Now what we will do is we will first run these tests in series using the command for. So we have a sim command inside a for loop. So it is going to run each of these 8 cycles in series, and each cycle is 10 minutes worth of flight cycle data. So these simulations are being run sequentially, one after the other, and at the end we'll see how long it took to run them in series. After that set of tests is done, we'll run them in parallel and compare again the duration or how long it took to run that set of tests. The purpose of these tests, other than we're testing the simulation under a range of conditions, and we're going to be looking at the power that is required of the generator. For this system level tests, we're using phasor mode. Again, this abstract mode with these abstract models allows the simulation to run very quickly. So we've seen the model blink a few times. We are almost at the end of our 80 minutes worth of simulation. And we'll see how long that duration took in the command window. A message will be printed at the end. So 80 minutes of simulation took about 90 seconds. Now what we'll do is we will simply change this to par 4, and then we will run the simulations in parallel. So now the same 80 minutes worth of simulations are being run, but those simulations are being distributed to 2 of the cores on my multi-core machine. We will expect that the duration, the time that it takes to run these tests will be slightly more than half of the time it took when running them in series. There is some associated setup time in order to set up the simulations on the different cores. At the conclusion of the tests, we'll plot the results, and that way we'll be able to see what happened on the different drives, on the different flight cycles over the 10-minute period. And though I am executing this one step at a time, we could simply let this script run and execute the whole thing. So we can see that the total testing time took about 50 seconds, which again is a little bit more than half because there is some associated setup time. And if we run these commands, we can see the plot of what happened during this 10 minutes of simulation. So we can see that for the most part there is certainly a level at which the generator is expected to run, and there are some spikes along the way depending upon different conditions in the circuit. At different conditions in the network. But you can see that completing 80 minutes of simulation in less than a minute would allow us to run lots of tests over long periods of time very quickly, and therefore really allow us to evaluate this network under a wide range of conditions. In this demonstration, we have seen how we can accelerate flight cycle tests using parallel computing. Now that we have completed this portion of our design process, we will see how we can automatically document the results of each step. In this demonstration, we're going to see how we can automatically run tests and document results. Designing a system is often an iterative process where we make a design change, test that change, evaluate the results, and then make a new design change. It often takes time to evaluate the results and document why we did what we did. We can automate that process using Simulate Report Generator. Using Simulate Report Generator, we can automatically run the tests that we need to run and then assemble the results of those tests into a report that includes an evaluation of the results, screenshots of the model, C, and MATLAB code. I'll now switch over to the model so you can see how this is done. Here is the model that we're working with. We have an aircraft power network with a generator, AC bus, AC loads, transformer rectifier unit, and a DC bus. We have a series of flight cycles that we would like to test. during those flight cycles, different loads are connected to or disconnected from the network. We'd like to run those tests, compare it to previous results, and include results from other analyses into a report. To do that, we will go to Tools, Report Generator to open the Simulink Report Generator. Here you can see we have set up the structure of the report. By pressing this button, we will run the report. So it is going to test this network under 3 different flight cycles and then take screenshots of the results and prepare that in a report. So you can see that we are running flight cycle 1, the results are complete and a screenshot has been taken. Now we are running flight cycle 2, the results are being generated, screenshotted, and put into the report. And at the conclusion of flight cycle 3, the report will be produced and displayed for us. So the tests are complete and we can see that the report has been produced. We can see that it includes screenshots of the model, including subsystems. There are plots of the test we just ran and results from previous iterations in the initial model. We have the results of a harmonic analysis, again done using MATLAB data. And at the bottom we have a table summarizing some of the information about the simulation runs. In this demonstration, we have seen how we can automatically run and document the results of tests using Simulink Report Generator. Here are the key points from our presentation. We saw many ways to configure our model so that we could balance model fidelity and simulation speed, including simulation modes and level of abstraction of the models. We saw how we could accelerate our simulations using optimization algorithms and parallel computing. And finally, we saw how we can accelerate our development process by automating analysis tasks using MATLAB.